Assalamualaikum warahmatullahi wabarakatuh. My name is Hanan binti Afi, and our group 5 will be presenting about single stage compressor. Our group members consist of Nura Azwa binti Kamar, Hanan binti Afi, Muhammad Amir Ashraf bin Muhammad Nazali, and Syafiq Hidayat bin Johan. So for the introduction, compressors are essential devices in many industrial applications designed to increase the pressure of gases by reducing their volume. In a single-stage compressor, this process occurs in a single compression step, providing an ideal system for studying the fundamental principles of thermodynamics. The experiment focuses on observing the conversion of heat energy into work during the compression process. As the gas is compressed, the energy required to perform the work is supplied by heat generated due to the compression, and by analyzing parameters such as pressure, temperature, and work input. The experiment aims to demonstrate the thermodynamic relationship and energy transformation involved. Understanding this conversion of heat into work is critical for designing efficient systems in industries like power generation, refrigeration, and pneumatic operations. This report highlights the theoretical and practical insights gained from studying a single-stage compressor in action. For theory, the operation of the compressor can be analyzed from the first law of thermodynamics that states energy supplied to the system work input is used in raising the internal energy of the gas and overcoming heat losses. Compression processes involve rise in both of the temperature and pressure of gas, hence energy in transit takes from heat. In a single-stage compressor, the compression process is normally modeled as isentropic compression. The gas is compressed without the transfer of heat either to or from the surroundings. Hence, it is reversible and adiabatic. Polytropic compression, this takes into consideration practical effects such as heat transfer and inefficiencies, and is represented by the polytropic equation PnVn equals to constant and PVn equals to constant, where n is the polytropic index. Some of the main parameters studied in this experiment include the following: work done, the amount of mechanical energy required for the compression of the gas, calculated through thermodynamics equations, temperature and pressure changes, and this will help in observing the relationship of heat to work, volumetric efficiency, the ratio of actual intake volume. Theoretical displacement gives an indication of how well the compressor fills the cylinder with gas, and the comprehension of these theoretical principles offers insight into how heat energy transforms into mechanical work in a single-stage compressor from the experiment.
So for the experimental setup, the first one on the left we have airflow meter, and then on top of that airflow meter we have the green inlet valve, and it is connected to the air chamber which has inlet air pressure, which is P1, and then the big machine on the top right is the electric power, and on the bottom right the blue one is spring balance, and it also have a motor, and then besides it has compressor, and it is connected to another air chamber which has outlet air pressure P2, and then it is connected to the red outlet valve. And also we use an item that is called tachometer, the orange one on the bottom. So this is the close-up look of our experimental setup, the apparatus that we use.
For the methodology, the first step to switch on the power, and next fully open the green inlet valve, and then record initial readings for all parameters listed in table 3.2.1 at the beginning of the experiment. use a tachometer to record the motor speed. Next, switch on the motor. Set the compressor outlet P2 to P1 bar gauge using the red outlet valve. Next step is to adjust the spring balance to ensure that the indicator on the motor is between the two black lines prior to recording any motor force values. And last step is record the temperature of the outlet air T2 at 1 minute intervals until two consecutive readings are the same. To stop the experiment, reduce the compressor outlet pressure P2 to 0 bar gauge using the red outlet valve. And lastly, switch off the motor and the first formula we use for this experiment is specific volume. Specific volumes equals to RT naught over P naught, where R equals to 0.287 and T naught is 29, but convert to Kelvin will be 302 Kelvin, and P naught is 104.2 kilopascal. Substituting the values, we got 0.832 meter cube over kg. To calculate the next, we use the volumetric flow rate formula, that is V in over 60 multiplied by 1000, and the volumetric flow rate is approximately 0.00433 meter cube. To calculate the mass flow rate, we need the value of volumetric flow rate and the specific volume. So the mass flow rate is approximately 0.00521 kg per second. Next is power out of the motor. This is the formula, and the value of power out of motor will be 576 watt. To calculate the energy added to air by the compressor, we use the formula Hc equals to mCp multiplied by T2 minus T1. And to calculate heat transfer, use the first law of thermodynamics for open system, that is Q equals to Hc minus W. Q is heat transfer, Hc is energy added, calculate, and work done on the air. Typically the motor output power. So these are the collected data from the experiment. After the data are collected, the energy added to air by compressor and heat emitted from compressor are calculated using the formula that are given.
So discussion for graph 1. So based on the graph 1, it shows the temperature T2 of the compressor increase with the time. During the experiment, there are a lot of heat generated that will increase the temperature and pressure. For the graph 2, it shows that the energy increase as time increases. The compressor motor will compress the gas, which increases the gas pressure and temperature. According to the first law of thermodynamics, the work done on the gas increases energy, resulting in a rise of temperature and pressure. And lastly, for graph 3, it shows a clear trend of decreasing heat emission over time. Initially, higher work might be needed to compress the gas, leading to higher heat losses. But as time goes on, the system may approach thermal equilibrium, where the amount of work required stabilizes, leading to reduced heat emission. So for the second questions, the energy that is being the input to the system when the system is heats up. So the first energy is internal energy. Particles inside the compressor will move faster due to an increase in kinetic energy. The second one is temperature rise,
which when the kinetic energy increases, the temperature will increase accordingly. And the last one is energy lost to the surrounding. As the temperature rises, it often loses some of this energy to the environment through mechanisms like conduction, convection, or radiation. This energy loss tends to increase as the temperature of the system becomes higher than that of its surrounding. And lastly, amount of energy lost as heat as compared to A, the work input to the compressor. So the amount of energy lost as heat is lower compared to work input to the compressor. And B, the heat added to the air. The amount of heat energy lost is higher than the heat added to the air at the beginning of the experiment. But at minute 10, the amount of energy lost is lower than the heat added to the air until the end of experiment, which is at minute 25. Based on this comparison, the energy and heat added to the compressor increases with time as the process goes by. So the conclusion that we can get from this experiment is, this experiment was to evaluate how quickly a single stage compressor heats up and analyze the steady state heat loss of a single stage compressor. So throughout the experiment, it being found that the outlet temperature T2 increased exponentially from 82 degrees Celsius to 150 Celsius, where it remains constant after 25 minutes of heating. When T is 25 minutes, steady state occurs as heat emitted, compressor remains at 576 watt. The energy added to air by compressor, Hc, also increases, while the heat emitted from compressor, Qc, decreases with time. If the compressor outlet pressure, P2, is reduced from 1 bar to 0.5 bar, the temperature will decrease by half. The heating time could be longer and the shape of the graph will be less steep.
So for the safety procedures, the first one is we have to wear the laboratory coat and also a closed shoe. This is to make sure that our whole body is fully covered and it will not get any contact with any chemical that we use. And then the second one is we have to report any injury to the lab assistant to prevent any unpleasant accident happen. And lastly, we have to handle the apparatus carefully to make sure that the apparatus will not break and also it will not be broken. So yeah, that is the safety procedures that we need to follow in order to do this experiment.